Welcome to this lesson on the Wilcoxon-Mann-Whitney test. Imagine you are a teacher trying to figure out if a new teaching method is better than the old one. But your test scores are completely skewed. Standard tools like the t-test might give you the wrong answer because they rely on averages. Today, we will explore a powerful alternative that uses ranks instead of raw scores, allowing us to compare groups fairly even when the data is messy or heavily skewed. So, why do we use ranks? The Wilcoxon-Mann-Whitney test is a non-parametric statistical method. This simply means it does not assume our data follows a specific shape, like a normal bell curve. Instead of comparing the average values of two groups, which can be easily distorted by extreme outliers, this test evaluates whether values from one group are consistently larger or smaller than values from the other. This makes it an incredibly robust and reliable alternative to traditional tests when your data violates standard assumptions. Now that we understand why this test is useful, let us look at how it works. The process begins by pooling all the data points from both groups together. We then sort this combined dataset from the smallest value to the largest and assign a numerical rank to each value, like first, second, and third. After ranking, we separate the groups again and sum up the ranks for each group separately. If one group has a significantly higher sum of ranks, it strongly suggests its underlying population tends to produce larger values. This brings us to the mathematical core of the test. The raw rank sum is hard to interpret because it depends heavily on the sample size. To fix this, we convert it into a standardized metric called the U statistic. The formula for the first group is U1 equals R1 minus the fraction N1 times N1 plus 1 over 2. The fraction calculates the absolute minimum possible rank sum if all observations in the first group were the smallest values. By subtracting this minimum, U1 tells us exactly how many times an observation from the first group was strictly greater than one from the second group. Similarly, we can calculate the U statistic for the second group. The formula is identical in structure, using R2 and N2. A beautiful mathematical property of this test is that the sum of U1 and U2 will always equal the product of the two sample sizes, N1 times N2. This product represents the total number of possible pairs you can form between the two groups. When performing the test manually, we calculate both U values and take the smaller one to compare against a table of critical values. Before we calculate an example, we need to know how to determine if our U statistic is significant. For very small sample sizes, we look at its exact null distribution using combinatorics. If there is truly no difference between the groups, any specific assignment of ranks is equally likely to happen purely by chance. By counting how many possible combinations result in a U statistic as extreme as the one we observed, we can calculate an exact p-value. This is perfect for small samples, but becomes computationally impossible as sample sizes grow. When the test tells us two groups are different, it means one group exhibits stochastic dominance over the other. We can calculate this exact probability directly from our U statistic. The probability that a randomly chosen observation from the first group, X, is strictly greater than one from the second group, Y, equals U divided by N1 times N2. Fascinatingly, this ratio is mathematically identical to the area under the ROC curve used in machine learning to evaluate classification models. It gives us a highly practical real-world metric. Let us see this with a concrete example. Suppose an agricultural researcher wants to compare the crop yield of two fertilizers. Fertilizer A is tested on 3 plots, yielding 12, 15, and 18 kilograms. Fertilizer B is tested on 4 plots, yielding 10, 11, 14, and 16 kilograms. Because the sample sizes are very small, we use the Wilcoxon-Mann-Whitney test. Our first step is to pool all the data together, and rank them from smallest to largest, keeping track of which fertilizer produced which yield. Continuing with our example, we now calculate the sum of the ranks for fertilizer A. The yields 12, 15 and 18 correspond to ranks 3, 5 and 7, giving us a rank sum R1 of 15. Next, we convert this into our standardized U1 statistic. We first calculate the minimum possible rank sum for fertilizer A, which is 3 into 4 divided by 2, equaling 6. Subtracting this minimum of 6 from our actual rank sum of 15 gives us a final U1 statistic of 9. Now that we have our U statistic of 9, let us interpret it. This means that 9 times out of the total possible pairings, a plot using fertilizer A had a strictly higher yield than a plot using fertilizer B. The maximum possible U is N1 times N2, which is 12. We calculate the probability of stochastic dominance by dividing 9 by 12, giving us 0.75. This means there is a 75% chance that a random plot with fertilizer A will outproduce a random plot with fertilizer B. That combinatorial approach is perfect for small samples. But what if we have a lot of data? Because counting combinations becomes too difficult for large data sets, we use a shortcut when both sample sizes are greater than 10. As the sample sizes increase, the distribution of all possible U values stops looking like a jagged set of discrete bars and starts to smooth out into a perfect bell curve, known as a normal distribution. This fantastic property allows us to use standard z-scores to find our p-value. To use the normal approximation, we first need to find the expected average or mean of the U statistic, assuming there is no difference between the groups. The formula is mu U equals N1 times N2 divided by 2. This makes intuitive sense. Since the maximum possible value for U is the product of the sample sizes, the average value we would expect to see if the ranks were distributed completely randomly is exactly half of that maximum. Next, we need to know how spread out the data is around this mean, which is measured by the variance. The formula for the variance, sigma squared U, multiplies the product of the sample sizes by the total combined sample size plus 1, all divided by 12. The number 12 is a mathematical constant that arises from the variance of a uniform distribution of consecutive integers, which perfectly describes a set of ranks. As sample sizes increase, this variance grows, reflecting the wider range of possible rank sums. Once we have both the mean and the variance, we can standardize our observed U statistic into a z-score. The formula is z equals U minus mu U divided by the square root of the variance, which is the standard deviation. The resulting z value tells us exactly how many standard deviations our observed U statistic is away from what we would expect by random chance. A very large positive or negative z value proves that the two groups are genuinely different. This diagram visually demonstrates why the large sample approximation works so well. The gray bars represent the exact, tedious combinatorial calculations for the U statistic. The smooth blue curve represents the normal distribution formula we just learned. As you can see, the smooth curve perfectly traces the tops of the bars, meaning the easy formula gives us almost the exact same answer as the difficult counting method. The red shaded areas in the tails represent the rejection regions, where the results are statistically significant. Let us apply this to a large sample scenario. Suppose a hospital is comparing recovery times for two physical therapy routines. Group 1 has 15 patients and Group 2 has 20 patients. After pooling and ranking, they find the U statistic for Group 1 is 210. Because both sample sizes are greater than 10, we use the normal approximation. First, we calculate the expected mean by multiplying 15 and 20, which gives a maximum possible U of 300. Dividing by 2 gives an expected mean of 150. Our observed U of 210 is higher than the expected 150. But is it statistically significant? To find out, we calculate the variance. We substitute our sample sizes into the variance formula. The product of the sample sizes is 300 and the sum of the sample sizes plus 1 is 36. Multiplying these gives 10,800. Dividing by the constant 12 gives a final variance of 900. To find the standard deviation for our z-score, we simply take the square root of 900, which is 30. Now we can calculate the final z-score to see how many standard deviations our result is from the mean. We subtract the expected mean of 150 from our observed U of 210, which shows our statistic is 60 units above what we would expect by random chance. Dividing 60 by our standard deviation of 30 gives a final z-score of 2.0. In a standard normal distribution, a z-score of 2.0 corresponds to a p-value of approximately 0.045. Since this is less than 0.05, the physical therapy routines are genuinely different. To summarize, the Wilcoxon-Mann-Whitney test is an indispensable tool in modern statistics. By converting messy or skewed data into simple ranks, it bypasses the strict assumptions required by traditional tests. Whether you are calculating exact probabilities for small clinical trials using combinatorics or using the normal approximation for large-scale data, this test provides a mathematically rigorous way to prove stochastic dominance. Its direct connection to the ROC curve cements its importance in both traditional statistics and cutting-edge machine learning evaluation. You now have a complete understanding of this powerful test.